Okay, in this one we have a railroad car, 10,000 kilograms, rolling at a velocity that's given, and then what happens is this mass is dropped into the car. So the total car and the mass is rolling along together. And the question is, what is the car's speed after the gravel is loaded? Now, of course, this is once again a momentum problem. It's looking at a set of before and after conditions. So we've got before and then after, and if we were to just kind of draw a picture of this, we would perhaps draw a picture of this railroad car. Not a very good picture, but we know that it is 10,000 kilograms. And after, we know that we have the railroad car on the same cart with 4,000 kilograms of gravel, so that the whole thing weighs 1,400 kilograms. 14,000, kilograms. This is mass 2, and mass 1 is 10,000 kilograms. And we know that in the end, the momentum must be the same. So this one that's moving at 2 meters per second must be balanced against this one, where we've got this new mass and now a new velocity. And if you had to guess, you can see that since the mass is bigger here, it must have a smaller velocity here in order for the products to be equal. So we want to know what that velocity is, though, V2. So we've got this V2 is an unknown value, so but we've got this simple equation now, and just solving for this velocity, we have, let's see, 10,000 times 2 is going to be 20,000 kilogram meters per second divided by 14,000 kilograms. You see the kilograms cancel, and so do some of these zeros. We got 20 over 14, which is equal to 10 over 7, which is equal to, what is that, 1 3/7. So that's nearly 1.5. We only have one significant figure, so I'm going to call this 1.5 meters per second is equal to that velocity. And if we look at that, we could see, well, this velocity is smaller than that one. Does that make sense to us? Does that make sense to us? Well, the mass is bigger, so since the momentum is constant, it probably is logical that the velocity would be smaller than the original velocity of this lighter car.